Pleasure to have Raghav Somani with us today. He's doing a PhD at the University of Washington, and he's going to tell us today about scaling limits of SGD over large net.
Hello everyone, thanks for coming to the talk. Myself Raghav Somani, I'm a PhD student at University of Washington. This is a joint work with Professor Zaid Harshawi, my advisor Sevongo, Shomik Pal, myself, and with Raghav Tripathi, who is Shomik. So I'll be talking about scaling limits of optimization algorithms over large networks as in graphs. The objective is generally to study large-scale optimization problems over the family of dense, weighted, and unlabeled graphs. By unlabeled, I mean the vertices are not labeled. Some very trivial examples, for example, are let's consider a graph G, vertex set P, X set E, n number of vertices, and the adjacency matrices. It's an n matrix. Consider functions like triangle density. So what it does, it counts the number of triangles in G and normalizes it. It's like a number between 0 and 1. And scalar entropy, which just takes the average entropy of all the edge weights. Very modest functions on any graph, independent of the size. And one application of such minimization problems is they come up very naturally as rate functions in exponential random graph models. And people try to look into problems like minimizing triangle density plus the entropy, and then they get interesting solutions to the various sample random graphs. Okay, so because we have the adjacency matrix in our hand, how would we trivially want to like minimize any function on the adjacency matrix? You just perform a gradient-based algorithm, and it typically does the job.
So AI is between 0 and 1. So
it could be weighted. So we are
between 0 1.
Yes, I'm only looking at weights between 0 and 1. It's fine. Yeah, but yeah, if you don't think about entropy, you can talk about functions all the other time. Okay, so minimizing functions like these. You could very well perform gradient descent on any adjacency matrix, n by n, or larger ones, whatever it is. The fundamental question we want to ask is, like, morally, what happens to our algorithms like gradient descent or stochastic gradient descent as n grows? And further, if there is stochasticity in the algorithm, does noise play any role? To look at space of graphs more closely, consider the symmetry in the set of unlabeled graphs. Look at the graph at the left, where it could be relabeled in many ways, at most 4 factorial, I think. And both these labelings are talking about the same graph. They correspond to different adjacency matrices as matrices, but they are still talking about the same graph, which is unlabeled in nature. And all these functions don't depend on the labeling or the way you label the vertices. So there is some symmetry happening inside this in this class of graphs. All right. So the motivation spawns from a toy problem. Consider the problem of minimizing the risk function of a neural network. In this case,
Like, just getting go back to last slide. Yes. So you said, okay, one can do some kind of gradient descent on the adjacency matrix, but then you said, okay, there's a lot of symmetry in the problem. So, so somehow you want to exploit that to help
exactly. So there are like in fact many adjacency matrices. It doesn't matter which one you choose and start optimizing them.
Right. There's no kind of a generic average of this A factorial which makes things easier.
Typically, it need not be, but because there is the symmetry in play, the idea or the model is to quotient it out and then look at it.
Quotient it also.
Yeah.
You will tell us now.
I'll come to that. Okay, so I was talking about this problem. You have a fancy looking neural network, 2-layer. What it does, so the purple neurons in the hidden layer, they compute some inner product and they apply a nonlinearity, and the output is just the average of these representations. And the risk function is defined with respect to a data distribution, with respect to the number of neurons. It's just the expectation of some loss function depending on the output of the neural network and the data set. All right, nice looking problem. So note that if you would like to optimize on the risk function Rn, the optimization process would look like a system of n interacting particles, where when I say particles, I mean the purple ones, which are the neurons here. And note that the output of the neurons, these neurons, the function, the output of the neural network is symmetric in the neurons. That is, if I take any permutation, commute my neurons, the output should stay the same. So there is a kind of a symmetry embedded in the problem. And if you exploit this symmetry, then like groups in Stanford and India have studied optimization problem on neural networks with the help of the theory of mean field limits and Wasserstein gradient. The attempt is to go beyond. I'll come to that.
So this X is a vector here, and you're assuming it has same distribution for each component. Is that right? That's how you get symmetry.
It could be a vector. It could have a joint density. Could have a joint distribution.
No, but you're assuming symmetry or some sort, right?
Symmetry in the hidden layers.
In the hidden.
Only. So that symmetry. So my particles are exchangeable. They are symmetric here, and my function is invariant with respect to computations on this. So, quotienting out this symmetry, you can use the theory of mean field limits and Wasserstein gradient flows to make sense of optimization problems as n grows to infinity or when it is very large. All right, so let's look at a simpler problem to make things more clear. Fix an n. Consider this function a very familiar one, which is average of the pairwise distance squared. If you look at it closely, it is nothing but the variance function of all the x's, and x is the n dimensional here. And not very hard to see that if I commute the x's, Rn doesn't really change. So it's permutation invariant. So again, the same recipe, I can perform gradient descent on every particle. Rn, let's say, is differentiable, and I can hope to solve this differential equation in some manner. And I can, for every particle I, it follows a differential equation. And that would be the particle gradient flow way of minimizing Rn, which is the variable of the xi. Then the trivial solution is that they collapse to the mean. Okay, so note that motion of every particle xi, by motion I mean x, how it is evolving, the x dot I, it depends on itself, and it symmetrically depends on all other variables, xj's. You can relabel xj's because summations are independent of permutation. There is symmetry inside this problem, which is a permutation symmetry. Now consider, for every n, I have this function Rn. They are on different dimensional spaces for every n. This is a common way to lift all these functions on a common space. There is just define a function on the space of probability measures, such that if it takes an empirical distribution, it evaluates to Rn of x. So now, if you give me any empirical measure, so like lots and lots of particles, I will just compute the empirical measure. And because things are permutation invariant, all you need is the empirical measure in order to compute the function Rn of x. So essentially, you want to minimize the function R independent of n, because now give me any n being finite or infinite, I can make sense of optimizing R. Now, the question again would be, as the limit n goes to infinity, can the particle gradient flow be characterized as the Wasserstein gradient flow of R on the space of probability measures on R? Is the example in the setup here? Cool. Okay, so coming back to the same differential partial differential.
What is the Wasserstein gradient flow?
I'll demonstrate that. Yeah. It's like a gradient flow on the space of probability measures on P of R, P2 of R.
So you just go back to the previous slide.
Yes.
So now you have this. I guess you need a notion of what x prime it means, right, in this general space.
This one?
Yeah.
This is Euclidean, so this is the usual.
No, but when you go to this Wasserstein settings, you have it right.
Oh, when I say Wasserstein gradient, there is a way to define Wasserstein.
There is a way to define.
Yeah, and it relates to x dot. It relates to the velocity field.
So you define a differential equation in the space of probability measure.
Kind of, yes, in the real sense.
So in this case, that capital R something like you take two independent samples from the uniform distribution and look at the expectation of x minus y squared.
Yes. Yes, just take the
E of x minus
just
y
take
x
the
and y are
expectation. Just take n to be infinity over here, which is the variance function. Okay, coming back to the same PDE, I mean, just add a fancy noise to it until things make sense. Just to demonstrate that your process need not be deterministic, it could be random, there could be external sources of randomness. And because of the symmetry, this SDE can be written down compactly in this fashion. The drift depends on itself, and the ensemble, which can be represented in as an empirical measure, like average and delta masses, that would be the drift function essentially, and the Brownian motion stays the same. So the question then to ask would be, so, okay, so for every I am having this SD in my hand, and there are n many SDs in my hand. Is there a law of large numbers for the system of interacting particles that can I compactly write a single equation or describe the evolution of so many number of particles as n goes to infinity? Maybe in the weak sense. It does, yes, and there is a law of large numbers, and on top of that, there is something called propagation of chaos. I'll come to that at some point. So it can be shown that as curves of probability measure. So you initialize that mu hat of 0, right? You initialize that mu hat of 0, and then as the system evolves, the empirical distribution also evolves, and let's call it mu hat n of t. Then as curves of probability measure, it can be shown that the whole curve converges to a limiting curve mu on the space of probability distribution as n goes to infinity in the weak sense over compact time intervals.
So one question is, so the way you define mu hat, it's still a random variable. So it's a random distribution. It's a random distribution. Because the x's themselves are random.
Yeah, but the delta one. But you can still compute the average of the delta mass of that.
Yeah, that's right.
Yeah, but
but this weak convergence, so it's like the random measure mu and n is converting degree to another random measure mu. Is that the thing? Or
yeah, in the weak sense.
So there are two things. So in the weak sense, the sense that the distribution, like you take any integrals of what function. But this is happening almost surely in other
Almost surely over that.
over the randomness of
Yeah, I should add.
yeah.
No, but this mu is a distribution, a deterministic distribution. In the
Mu is
Random also.
it's a curve of distribution.
No, curve indexed by time t.
It's
Right? So each state is a given fixed probability distribution.
It's a fixed probability.
So it's not
In the limit, it will come.
So mu hat is a random, but mu is not.
yeah.
Okay. And then
Okay,
So
so
if you be like the empirical methods converts it to
That's right.
exactly. There are some extra and they
but on point by
histograms converging to small distribution.
That's all it is.
It's like an evolving histogram converging. Okay, so coming to the law of large numbers, it can be compactly written in terms of what is called a McKean-Vlasov SD, and following it says. So we saw this SD previously in the past slide, where we had this kind of an SD for every I. But this can be put to the limit, and you can say that if you randomly sample a particle,
but so there's a mu hat at each time t also, right?
yeah, as curves.
As curves of probability.
As curves, they compactly
So the test functions are functions which can go over, so they're functional.
at every time.
And
so it's basically mu hat n of t. So
Yeah,
you're
so
saying
The supremum of the distance over the
yes.
uniformly the whole
Uniform
uniform. It's I use this notation for as curves. Convergence as curves. So yeah, the SDs that I had earlier, they admit a limit through the McKean-Vlasov SDs, and they can be described very similarly. Is what you would expect. It's the same SD, but the empirical one is represented by the ensemble, which is the law of the randomly chosen particle X. And X and mu are set to solve. So this is pretty well studied in literature. And for this particular example, it is said that it solves a granular media equation, and it's a Wasserstein gradient of a certain kind of a function. As a toy example, let me just demonstrate what I mean. Let's consider the same variance function, and I'm just considering a fancy looking data set over here, I will try to emulate the SD on this ensemble of particles. They are evolving according to that SD that we saw in the past slide. For every particle, it's following the drift, and I'm adding a Brownian motion. And as you see, and also as you might expect, that this converges to a distribution in the limit. N is pretty large, N is like 50,000.
But N is fixed in the simulation?
N is like 50,000.
But it's fixed.
It's fixed.
So T is very.
Yes. So it seems to be converging to something which we already know. This is where it converges after a long point of time. That is roughly looks like normal of 0, identity. And we for a fact know that this is nothing but the minimizer of the variance function plus the entropy function. So what the Wasserstein gradient flow tells us that the evolution of mu t is nothing but the Wasserstein gradient flow of the risk function regularized with entropy, which is because of the Brownian motion. And this is a these are two different compact ways of describing the limiting evolution of the system of interacting particles. So I hope this simulation made it more clear. Let's go on.
So the colors I should think of as like so each
this is the MNIST data set. Every
yeah, so
other
but in your formalism, each xi has a color which is not changing with time.
colors are not. This is just saying that even the colors get mixed up.
Yeah, but the colors are not being used by dynamics. The dynamics is blind to that. But yeah, in the
They all get mixed up. So a randomly chosen particle could be of a random color.
yes, that's yeah.
So if you have in each particle, they are independently performing a asymptotic process with this Gaussian as the stationary measure. This is also what we call the same PDE, right?
Every particle will satisfy the particle level PDE. But my
But your thing is some interacting process, or
it's an interacting process because we saw the velocity field in right?
Because mu is also there in the right hand side.
Yeah, the velocity field something looks like this. It depends on itself and all other particles as well.
okay.
And what I did is to just simulate this for every I. That's all I did for all the 50,000 points.
Okay.
Yeah, and I'm able to see that as because N is already quite large, I see an limiting effect, and which can be described consistently with respect to these two notions of the limit. I can compactly write down what the limit of a randomly chosen particle is.
So this is basically exactly each particle does the Austin will get
Independently.
Independently, and its motion depends on everybody else
Okay.
symmetrically.
So earlier you had Brownian motion indexed by I for each particle. Now
This
we-
convergence is in the weak sense. So there exists a probability measure under which there is a Brownian motion, so that you can couple them.
But this Brownian motion is different for each particle. Right?
It will be the same.
It will be the same.
Yeah. This is in law. This is in the weak sense.
Okay, because it's in the top.
Okay, coming to the beast. Let's look at, so we looked at the two-layer neural network example, right? And we know what the symmetry over there is. Just if we look at the deeper version of the same network, it has many layers, many layers. And there is again a symmetry hidden inside this problem. The computation is the same way. You take x, compute x1 using some nonlinearity functions and keep on doing that. And you output the network's value. So for every layer, I can permute the neurons and the output still stays the same. So we have a very similar looking symmetry, but we need to be very careful. If you permute, let's say the LH layer, the rows of the L-1th and the columns of the LH layer, they get permuted by the same permutation. It's not exactly that, but still there is a symmetry group in play over here. And if I talk about neural networks, at the moment I just want them to think of as computational graphs at this point. So this is just a computational graph. These are edges, these are vertices. There is some symmetry inside this graph, some unlabeled kind of symmetry inside these graphs, and the function is invariant with respect to that symmetry. One thing very similar that we saw earlier. Okay, yeah, permutation symmetries within each layer keep the output of a neural network and change. And optimization problems over graphs are invariant under the permutation of the vertex labels. because the network is invariant.
So earlier when you said you were going to optimize over graphs, I mean, here it's weights of the edges, and there I thought you were talking about edges being different, but
These are weighted edges.
yeah, so
but
that's what you meant even earlier as well.
Yeah.
On the M1 and N2, that will go to infinity. In this setting,
As the size of the graph goes to infinity, I'll ask the same question. Right. So, okay, we want to quotient the symmetry out. Let's see how we can do that. So essentially, we want to think of a space where the symmetry is quotiented out, which means I will recognize all the permutations of A. By permutation of A, I mean use a permutation to permute the rows and the columns similarly as the same element. So maybe there are infinite ways of permuting A, and I will recognize all of them as the same element. And there is no reason to believe that this will have an Euclidean geometry. You cannot just add subtract equivalence classes. Again, the same question. So what happens as n goes to infinity? How do Euclidean gradient descent and stochastic gradient descent behave under the presence of such a symmetry? And can we extend the theory of mean field limits and Wasserstein gradient flow in accommodating this newer symmetry that we have seen here? Right. So here I will explain the setup and at the end some results. This is kind of a rough tutorial and the path what we have taken in order to build this. Okay, so what do we need? We saw earlier that we were able to lift all the functions Rn to a common space P of R. And on this space, which I'm calling embedding, on this space, I can maybe make sense of all the problems together. So, okay, again, what is the common space here? I want to lift all the Rn's which take adjacency matrices, real numbers, and what is this R? On what space should that be defined? Okay, in the space of probability measures, we saw that there is a topology, and there is a topology of weak convergence on the space of probability measures. What is the notion of graph convergence here so that I can extract the topology from it? Next question would be, okay, do we also have a complete metric space? We have a metric space on probability measures, the Wasserstein 2 metric, popularly used one. Is there also a metric which I can use on the space of graphs or maybe limits of graphs in some sense? And once we have a metric space, can we make sense of gradient flows on that metric space? Generally, gradient flows have been studied for arbitrary metric space under nice conditions. So, do we have gradient flows with respect to this metric, which I will define at some point? So, this is the recipe, and let's say how can we proceed to the final object. Coming to the embedding, graph limits have been studied extensively. They were extensively studied by Lovász and Szegedy, and they are called graphons. And these objects, you can think of them as limits of graphs, and they capture the exact symmetry that we have been talking about, the graph isomorphism symmetry. Let's see what they are. But before that, let's go step by step. Consider a graph G, which has an adjacency matrix A. It's just a symmetric matrix. Just look at this matrix as an image. I mean, by image, I mean a function on 0, 1 square, and put a step on it so that it is the same as the symmetric matrix. Note that this function is on 0, 1 square. So I am normalizing the spatial dimensions and putting the values as using step functions. And because step functions are dense in measurable on the space of measurable functions, this allows me to take a certain kind of limit. So when I'm taking limit as n goes to infinity, it does give me a measurable function at least. That's good news. As an example, look at this R graph. I just borrowed this example from this book. It has an adjacency matrix structure. Note that this is labeled at this point. I have to remove the labeling. And if I just look at this adjacency matrix as an image, it looks something like this staircase kind of thing. So,
so this adjacency matrix will only holds for symmetric matrices, right?
Yeah, symmetric. Yeah, at the moment you can we can deal with symmetric, but unsymmetric ones can also be different.
I mean, you need PSD. You need your symmetry. I mean, adjacency matrix to be positive symmetry. Otherwise,
It can be any matrix. I mean, this process can be done for any symmetry vertex.
This is not linear for.
Yeah, it's not exactly adjacency matrices. The edge weights are at the ijth.
Yes. Okay, but this is an undirected graph. So yes, okay. So
That's why it's
okay.
You can also think
Okay,
about direct
right.
graphs or
So we-
negative algebra or something. And the same philosophy will hold. You can create kernels out of a matrix just by rescaling the spatial dimensions, the i's and j and the j's to 0, 1 square, and looking it as an image or a function. Like speaking.
Okay, I don't understand. So how is this image constructed from the matrix?
Here the origin is here, but here the origin is here. I'm looking at the function.
Oh, yes.
It's very easier for them.
Okay.
I don't know why it's chose the origin over there.
Well, because
The CS guys.
yeah, I gave up a while ago.
Alright, so writing this as a definition.
So who came up with the name graphon? That goes to say graph.
Lovász. I think the way it is named is graph function.
Oh,
I think that's the way Lovász thought about naming it. Just a guess. Okay, so bringing all of that in a definition, a kernel is nothing but a Borel measurable function, W. It takes numbers in like points in unit square and maps it to, let's say, -1, 1, and that it is symmetric to x, y, z, y, just like I just mentioned. So now we have a common embedding, but we used kernels for vertex labeled graphs. We want to throw away the labeling, right? Because there is a symmetry that we want to exploit. So what we want to do essentially is we want to recognize matrices or kernels up to permutations. Relabel whichever way they want, they should be the same object because they are just unlabeled graphs. So what we do is we will identify two kernels, W1 and W2, to be weakly isomorphic. If one can be obtained by relabeling the other one. So if I can obtain W2 by relabeling W1 using some measure preserving transformations or some permutations, then I will say that W1 is equivalent to W2 and I can reason about equivalence classes now. This is an equivalence relation. Once you have equivalence relation, you can think about the coefficient space, and this coefficient space is nothing but the space of graphons. And any element, any graphon in the set corresponds to an unlabeled graph, at least in the and Lovász and Szegedy were awarded the following prizes for developing this theory forward. So this was in 2006. Right. Okay, nice. Let's try to understand the topology a bit better. We saw this kernel, a staircase kind of thing in our previous slide. You can very well imagine that if you take n to infinity, this is how it's going to look like, right? No surprises here. Let me ask a question now. Yeah. Consider this graph here. Its kernel representation looks like a chessboard to me. And what do you think if I increase h to infinity, or basically take n to infinity, where do these graphons converge? If anybody has a guess, they can throw. Does it converge to like all black, all white? Maybe fractal of acceleration.
We use the word discrete, and then it will become like this. Like,
Yes, that was quick. Correct. Relabel them in a different way, and you will find that this kernel corresponds to a relabeling of this kernel. And now, if I want to portend the symmetry out, I should think of this kernel and this kernel as two representatives of the same graphon. So again, the moral of the story is that both A and B are the same graphon, but two different kernel representations. It's just a matter of labeling and nothing else. These two are the same object. So when you take n to infinity, you get the same thing. The speciality of this example. Okay, so this is the embedding space. Okay, coming to the topology, it's a question on topology.
So yeah, so these two pictures you showed us and you said that they are similar. How does one kind of know that all pictures are similar and they're different?
If there
Is
exists,
no, but is there an easier way of kind of without the definition?
I'm not sure. Maybe in some cases you can do this. In general, you have to search over all.
Kind of simplification that you got by
Computationally asking, or maybe
no, just visually, I mean, you're getting a sense of.
no, but you don't care about that. There is no representative kernel corresponding to it. There is no canonical kernel. if I give you an unlabeled graph, there is no canonical way to label it. You start from top left or bottom right, doesn't really matter.
Yeah, I mean, somehow I thought it'd be more satisfying. The theory was, all of these are similar, and you say, oh, that's why they're similar. But
It could be hard to check. For
seems
example,
complicated. Yeah.
when I saw this example first, I thought that I think it could infinitely pixelate and maybe it's the half graphon, all half, because half 0.5 is between 0 and 1. But I got puzzled, and this is the new way to think about it.
So the measure of black and white are the same.
But internet should be hard, because graph isomorphism is hard. So
Yeah, that's always there. That will always be there. Okay, so coming to what is the topology that we want to put on the set of graphs?
Unless the name will last no more, right? Then
No, unless you're Babai. So Babai recently shows that graph isomorphism can be done in quasi-polynomial.
Oh, yeah. So
Yeah, but I don't know, it's probably
a few years ago.
yeah, okay, few years ago.
that's a different question.
There was a
than
question
what we-
from the proof, right? Or is it?
And then, yeah.
But I would think that there are probably 20 people in the world who understand the truth.
Two is
Okay. Okay, so we have a set or a common embedding space which can correctly make sense of limits of unlabeled weighted graphs. But what about the topology that we want to put on this set? Graphon at the moment is just a set, it's not a space yet. So in order to make sense of that question, we want to understand what graph convergence means, because once we make sense of graph convergence, we can make sense of topology. And to make sense of convergence, we want to ask a very simple question. If we have two graphs G1 and G2, when are they similar? What is the notion of similarity or closeness? I just stole this slide from Christian Borges, pardon, but let's say a combinatorialist takes this problem in hand and we ask this question. You have two graphs, G1 and G2. What do you think? Are they close or not? What they would do is that they will check local properties like subgraph count. They will look at if the edge density in these two graphs are the same. Maybe yes. Our triangle density is same. Maybe yes. Our cleave density is same. Our cycle density is same. I can ask all sorts of questions. If all these local properties are similar, the combinatorialist might say that the two graphs are close. Maybe they don't know how to quantify it, but there is a motion at least. Next from a statistician, they say that this is a lot of counting to do. What I can do is I will sample subgraphs from large graphs and check the distribution of the subgraph that I sampled. If the distributions of, let's say, k by k submatrices, if they are same on RK square, then I will say that two graphs are same. And if it's true for all k, I will say that the two graphs are same. Now notice that these are very local properties. They seem to be local properties. And a computer scientist would say, I care about global properties. Like, what about max cut? It's a global property. I will say that two graphs are same if the max cut values of the two graphs are similar. Very valid. Now, a physicist might come and say that, okay, everything is static in this world. I want to do some dynamic on this graph. I will put some statistical physics model and check if the free energy is the same in the two graphs over some statistical physics model. It very well turns out that this famous 5-author group showed in a sequence of papers that all these notions of convergence or closeness are equivalent. So it hints at a very natural topology which is present on the space of graphons. And we will see what that is. Okay. We will say that a sequence of graphs converge if the limit of all f subgraph homomorphism densities. So initially, if you remember, I had this H triangle in the very first slide. If the limit of these numbers for every f, if they exist to some real number, maybe we don't care what they are, but if they exist for all simple graphs, I will say that Gn converges. It's the first definition that a combinatorialist might use. And
What is A?
Sorry?
What is A? That's A.
F is the set of finite simple graphs.
Okay.
These are like test functions. So in order to check. Yeah, all enumerate all of them, they are countable many. And if all these numbers converge to some real number, they have a limit. I will say that the graph has a limit. And this actually captures weak convergence notions over unweighted graphs. Unweighted graphs. So this is like checking distribution from all finite subsamples on the run. And this topology can be extended to weighted ones also. You just extend the definition to weighted ones. You can make sense of this definition. That is graph convergence. And this is very analogous to the topology of weak convergence that we are very familiar with over probability measures. We are looking at certain test functions, and for all certain test functions, these numbers happen to converge. I will say that my graphs are converging. So Friesen-Fanon in 1999 showed that this topology can be metrized by something called a cut metric, and this is where the relation between local properties and global properties come up. I will not explicitly write the definition of cut metric, but it has really interesting properties at least that is worth discussing. The topological space of graphons with respect to this cut metric, which is now a metrized space, it turns out it is a compact metric space. And compactness is a very nice analytical property to have. It uses the famous Seminer's weak regularity lemmas, and in some sense, you can say that this space is not that big. It's not really wide.
So I still don't want to let go. Yeah. So I think exactly this, that if I want to say that two graphons are close to each other, can I still say that graphically in some sense?
Two graphons.
Yeah, are close to each other.
You can compute these numbers and compute the metric.
No, I don't. Is there at all a graphic you were saying something? No.
Graphic, a
Pictorial.
unified graphic principle, I don't really think there is. So because the space of commutations becomes so huge that it.
But if there's an instance in one graphon in the equivalence class and there's an instance in another one and they are kind of close, and then that
You have to permute the other one and match them appropriately.
Yeah.
If you're able to match them up to maybe a few edges, you will say that two graphs.
That's all right. So that's still simple, right?
Yeah, that is exactly what we want to capture, graph similarity. So the first example that comes in our head, we have this sequence of Wasserstein graphs, G n half, n is growing in size. To which graphon does it converge to? And if you use the definition of the topology, you will find that the kernel or the graphon that it converges to, it's the all half graphon. So whichever way you permute it, it doesn't really matter, it's the all half graphon. So all the triangle densities here, where they will converge to P cube, and here also it will be P cube, like half cube. So in that sense, and in this topology, the sequence of graphs converges to all half graphon. Makes sense. Okay, so now we have an embedding, we have a topology. What about the metric? And it turns out that topology is also metrizable, but we want an even nicer metric to work with. So space of kernels, at least, you can think of it as a subset in the L2 space on 0, 1 square. Right? It's a subset because its weights are bounded by -1, 1. So it's essentially a subset of the L2 space. It comes up with its own inner product and so on. And we can define something called an invariant L2 metric, defined by Janssen in 2016. It is very similar to, for example, you take two graphs, you find the best coupling of G2 with respect to G1, subtract the adjacency matrices, and compute the L2 number. So, and if you are any familiar with the optimal transport literature, if you know about what Gromov-Wasserstein distance is, this metric is exactly the Gromov-Wasserstein distance between the two kernels if you view them as metric limit spaces. So, okay, so this is another metric, and it turns out that this metric is strictly stronger than the cut metric. That is, graph convergence need not imply convergence in delta 2, the invariant delta metric. For example, the Wasserstein graphs don't converge to anything. Because the variance component, if you're subtracting them, Aij and Bij, whatever coupling you do, because they're independent, you will always have the variance component in term.
So how is W1 a metric?
And your base space is 0, 1, your measure is Lebesgue, and the metric is W1 x comma y. If dxy is equal to W1 x y.
But that need not satisfy the triangle equality. The graphon need not satisfy triangle equality.
It need not, but let's say it does. So if you are familiar with Gromov-Wasserstein,
so that doesn't require it to be
it's
metric.
not required.
It just needs to be some.
Yeah. I don't want to write the expression, so this thing was. And this is very analogous to the Wasserstein 2 metric that we use in probability measures. There also you want to find the optimal coupling between two measures. Here you want to find the optimal labeling of two graphs, so that means you subtract and take the expectation. That's the metric value. So what we show here is that
Is that the same thing as what you're saying? So like you take arbitrary this measure to the transformations apply to W2 and then look at the and then look at what? So then look at WX1X, so you independently sample from
you can think of it that way. What is the expected value of the difference?
different between
You optimally couple. So for this metric, why is it important that we show certain properties will help us to construct gradient flows with respect to this metric? So we show that this metric is first of all a geodesic metric, which makes this space a very nice space. And this is just like what we have in the Wasserstein setup also. The space of probability measures with respect under the Wasserstein metric is a geodesic metric space. And here we are able to show the same thing. So if you have geodesic, you can make sense of geodesic convexity on the space, on this metric space. And this demanding geodesic convexity is easier because this is a weaker condition than Euclidean convexity. A function could be geodesically convex but not Euclidean convex.
Your example, what does geodesic convexity mean?
Geodesic convexity means that if you have a geodesic, you want to ask for the convexity relation along the geodesic. The lambda parameterization is along the geodesic. So in that way, you can make sense of what geodesic convexity is. So the function with that geodesically convex are superset and are strictly bigger than the set of functions which are just Euclidean convex. And this is because of the symmetry and the redundancy in the labeling. Once we have geodesics, once we have a metric space which is geodesic, there exists a notion of gradient on the space also. Not precisely, but there exists a notion of gradient, which I'll explain in a second. And once you have something called a gradient, maybe we can also construct gradient flows, which we do on the space of graphons with respect to the delta 2 metric. So the gradient, basically the steepest descent, has to be taken with respect to the delta 2 metric, which is L2. And you might guess that it is very amenable to Euclidean gradients now, because Euclidean gradients are also L2 gradients. Right. So what's the notion of gradient? Say you have a function R takes a kernel and it gives you a real number. Our notion of gradient is what we call Frechet-like derivative. Sorry for the abuse of notation here. And dr of W, which is the Frechet-like derivative of R, and evaluated at the kernel W, it is nothing but the first order linear approximation of the function if you view the kernel as an element in L2. So L2 has its inner product structure, so you can extract the Frechet derivative out up to some boundary conditions. That is an L infinity function, so to say. That is a notion of gradient. Again, coming back to this example again and again. Homomorphism density function of the triangle. How would you compute it? For example, sample 3 vertices from uniform 0, 1. You have spatially normalized everything, so it is enough to uniformly sample U1, U2, U3 from 0, 1. Check if U1, U2 is connected, U2, U3 is connected, U3, U1 is connected. Take the expectation, right? Which in integral way looks like this. And it is not a hard calculation to check. If you want to find the first order linear approximation of this function, it looks like something like this. This is the Frechet derivative of the triangle homomorphism density function of the triangle evaluated at kernel W. It looks like this. If you see it closely, it looks like matrix multiplication.
So in what sense is it not a Frechet derivative?
You're asking what does this like mean?
I mean, they said you're somehow not scoring it Frechet, so nothing different.
Yeah, because the space of kernels is a subset. So at the boundary, you need to take care of.
Okay, in that sense.
Yeah, in that sense. So we didn't want to just do Frechet derivative. Maybe there is a better word you have on these sessions.
Frechet on.
Yeah. Nothing important, I think that can be get away with. Okay, so we have a notion of gradient. What about gradient flow? Do they even exist? So let's say you again have a function R on graphons, and let's say it is pressure differentiable with respect to what we define derivative. That at every W there is a pressure derivative. So let's also assume for a moment that it is geodesically semi-convex with respect to our invariant L2 metric. So this allows us non-convexity also. And let's say you start your gradient flow, you want to start your gradient flow from a graphon W0. So the gradient flow curve WT of the risk function R on the space of graphon simply just looks like this. You just follow, you start at W0, you follow the negative pressure derivative from 0 to T, and that is it, as you would expect. Now follow this inside the graphons, and when you hit the boundary, you just project it. Let's see, add constraints to contain. Okay, so gradient flow now exists. So everything that I spoke about in the past like 10 minutes or so, everything is on the infinite dimensional sense, right? How is it even related to our Euclidean algorithms? This is very similar to how Wasserstein gradient is related to the Euclidean gradient. Let me say how that is. Consider the example Rn of x, which is just compute the mean of the n particles. It's Euclidean gradient because it is normalized by 1 over n. It will be the all ones vector times 1 over n. 1 over n is the mass of every particle. And if you lift all the Rn's to the space of probability measures, it looks like just the mean function, integral x cubed. And if you are aware with how to compute the Wasserstein gradient, the Wasserstein gradient of this function R is nothing but the constant function 1. And now you see a relation between them. So in some sense, n times the Euclidean gradient is equals to the Wasserstein gradient of the lifted function R. So this is the bridge between Euclidean gradients, which we use in Variance, and the Wasserstein gradient that we can use analysis. A very similar example here, consider Rn to be the average of the edge weights, 1 over n squared summation an ij. Its Euclidean gradient is the all ones matrix divided by n squared because it is normalized by n squared. Normalization carries forward. And if you lift all these functions Rn, R1, R2, R3, Rn to R, it will look like the integral of the edge densities. Not very hard to see the way we define W from axis symmetry system. And if you compute the first order approximation, which is the pressurized derivative, it will be the all ones function. So here again, you have the relation between the Euclidean gradient, just multiply your Euclidean gradient by n squared. In some sense, it will give you the pressure derivative back. So maybe gradient flows on graphons can be obtained as scaling limits of the Euclidean algorithms, Euclidean gradient descent up to numerical errors. And that is what our next theorem will tell you. Let's assume that R is a function and its gradient flow exists, and it looks like this. W2 is a gradient flow. You start at W0, and WT is it just follows the negative pressure derivative. Okay, this exists at the infinite level. But now let's try to approximate it or try to mimic this gradient flow. What we can do at best is try to run our Euclidean gradient descent algorithms. But for now, let's take it close. On every Rn, what it does, it takes a matrix and returns you a value, a real number, and it starts at Wn0. It's an n-minus matrix here, the graphon version of it. And the gradient flow will essentially look like Wn of t. It follows a negative Euclidean gradient up to pointwise projection that we want to issue. So what the theorem will say that if your initializations converge to W0, then the whole curve Wn as n goes to infinity, it converges in the cut metric to the gradient flow curve in the left. There is a consistency between the finite and the infinite volume. So yes, this convergence happens in the graph sense again as n goes to infinity. It's very nice to have. So essentially, what are the results at this point of time? Under suitable assumption, we show that if the step sizes of your algorithms go to 0, and if n goes to infinity, Euclidean gradient descent over finite dimensional Euclidean spaces, which we run on our computers, they converge to a gradient flow on the metric space of graphons. there is a consistency between these two words. Not just gradient descent, but this the same thing happens for stochastic gradient descent. Euclidean stochastic gradient descent algorithms, or even any other stochastic approximation algorithms which are unbiased, over finite dimensional Euclidean spaces n by n, they converge to the same gradient flow that you obtain here on the metric space of graphons. So the stochasticity is kind of washed away at when n goes to infinity. That is good news. Let's look at even noisier versions of LGD. Let me demonstrate what I mean by that. In the machine learning setup, what you have is you have loss functions and you have random data points, and your risk function is defined like this. So what you could do is you at every step k, if you have w, k, and n, you take a negative step with respect to the step size tau n, follow the stochastic Euclidean gradient because there is some noise there. And maybe you want to add an even bigger noise, which is just Gaussian noise, appropriately scaled, of course. And then you project this. So this covers a wide variety of algorithms. What we show is that if the initializations of these algorithms, they converge to some graphon W0, and if the step size go to 0 and then n goes to infinity, then there is a limiting curve to which these algorithms converge to as processes. Which means that there exists a unique curve gamma, evaluates t to gamma t, such that as curves, all these iterates as n goes to infinity, it converges to the curve on graphons in the graph sense, by which I mean in the cut matrix sense, as n goes to infinity almost surely. This almost surely is a randomness due to psi and Gaussian.
When you say gamma, it's a function of t. You're not talking about that as t goes to infinity. It's not stabilizing and
no. So this convergence is only over compact time intervals. There has to be a finite horizon, and until then, you can hope for convergence.
So you've not kind of worked in that direction where as t goes to infinity is the
Actually, we haven't specifically analyzed that because it depends on the risk function. If the risk function has nice contractive property and so on, and maybe in the limit, if you're converging to a point, some stable point, that should be the case. That is an expectation. But generally, if you have any velocity field that you're trying to emulate using your algorithms, that is all you can show them. Fix a finite time horizon, your curve will converge to.
Now, all of what you're saying fits into this one layer neural network, right? You have these symmetries. So there, are you saying something interesting about the limiting object, gamma of t?
Gamma of t will be a neural net in that sense.
So in the limit as
In the limit,
goes to
yes.
infinity,
It will be a graph.
it'll be a graphon.
Yes.
But more than that, I mean, anything useful can you say?
So there is a question of depth there. I'll come to that question at some point. So, but still, I want to think of neural networks as computational graphs, and as graphs, they do have a limit.
No, the fact that they have a limit, maybe it can be identified. How is it useful? So,
The graphon limit.
first of all, is the limit identifiable? Like then it would be useful to identify.
So it's just a sequence of graphs. So sequence of graphs can have accumulation points or limit points. So let's say it has a unique limit point. So that would be the so if your neural network is already very large, it is sufficient to look at the graphon limit and do analysis with that. Because in the limit you have very nice properties which pop out. I'll describe in this slide.
Yeah, that's what I'm asking.
I'll describe this in this slide. Okay, so coming to the McKean-Vlasov type of limit that we also saw earlier. Fix a property space and a Brownian motion on the property space. Sample two random vertices from uniform 0, 1. By vertices I mean because it's spatially normalized. So you sample two vertices, random variables even. We say that just similarly previously, like previous setting, we say that X and gamma solve the McKean-Vlasov type SDE. If you look at the set where if you have labeled your vertices capital U and capital V as small u and small v, on that set, there is a single SDE which can describe the limit. And that goes like this. The random edge, the drift of the random edge is nothing but negative of the Fletcher derivative of the ensemble. It depends on all other particles, all other edges, basically the whole graph, evaluated at the endpoints of the edge between U and V. That's the drift, and everything else stays the same. So, and The way to recover this limit would be just look at this random variable x, which is like the random edge between u and v, condition it on capital U and capital V being the labels. That will give you the gamma kernel. And you just symmetrize it to obtain the gamma graphon. I mean, quotient out the symmetry and you will get the gamma graphon. So the set of these two expressions are essentially capturing the limiting behavior of interacting processes on interacting graphs, interacting processes on graphs. Okay, so what are the two phenomena that I want to highlight here? One is our mean field interaction. Again, as we saw earlier as well. Any edge weight x, I'm just color coding them for your convenience. The effect of all other edge weights, which is the whole graphon, the ensemble, on its evolution is invariant under vertex labeling, and what we saw here. And next is propagation of chaos phenomenon, which is pretty interesting. So in the limit, what happens is that let's randomly choose m vertices from the graph, and you can imagine a submatrix of n by n. And every edge weight in those m square many edge weights, they will become statistically independent as n goes to infinity. So these are some properties that you expect in the limit, and this property in general is known as propagation of chaos, which is exhibited here. Okay, some example. So because we are studying optimization processes on graphs, we can look at certain questions in extremal graph arena. One of the famous theorems is Durand's theorem, and a special case of it says that the n vertex graph which doesn't have any triangles but has the maximum number of edges, it has to be a complete bipartite graph. Right? Not very hard to guess. So can we recover this theorem statement through an optimization process, because we have a toolkit now? Can we recover this theorem? Yeah. So let's say I initialize. So let's say as n is growing, I'm initializing my kernel in some sense. It's very pixelated because n is 7. I make it more finer and finer so that it looks smooth. So in some sense, in the graph sense, this sequence of initializations has a limit. I will run the gradient descent algorithm as animations here, and you will see that they will be able to recover the solution of Lovász theorem, which is a complete bipartite graph. Here it is not clear. So you can now guess what the limit is. Up to relabeling, up to permutations, you get the 2x2 structure, which is the solution of optimization problem that constrained on the fact that there are no triangles, maximize the number of edges. And what I did is I just applied gradient descent. What I know. I can use a computer.
So does it say anything about the training the neural networks in GDs? For example, it does converge to a global optimus. For
All these
example,
processes at different ends, as n is growing, the whole curve is converging to smooth curve on the space. That is what it is.
yes, but here you do converge to a global optima, right?
This is the property of the method. It has the attractor, so it does converge on there.
And this property might not be present in
You could converge to maybe standard
Okay.
for who knows.
Yeah.
But the point is that the curves converge. Wherever is the limiting curve going, I don't really know. That depends on the example,
Okay.
the application. But as curves, all these algorithms converge to a limiting curve. But with some. That is why I told you the animation, because the trajectory that these processes are taking, these trajectories are uniformly converging in the
Right. No, I mean there is a recent results not so recent saying that all this local optimas are good for neural network.
That depends on the application and analysis. What
Right.
property does it?
Okay, so it doesn't say anything about this.
So this function that I'm optimizing, we can show that this is semi-convex.
Okay.
Maybe that is why you are able
I
to
see.
see that.
I see.
But in general, you have to analyze
The function.
geodesic analogs of the same properties that people use in optimization, like geodesic convexity, geodesic smoothness.
Maybe each member in the equivalence class is local.
Yes.
Is that what?
Yeah.
Well, in this now, suppose because when you discretize and solve all this, you're solving maybe a finite graph problem. Exactly, what are you doing? Can you say something in?
I have a function Rn of A. I'm just following the gradient.
It's okay, you can't describe in terms of nodes what I'm doing at each edge or something. It's not that simple.
It's just these are just real numbers. I'm just following the gradient.
It doesn't have an interpretation.
That is all we do in our numbers. Okay, that is the deterministic nice algorithm. Has a here I do the same thing for the same initialization. I will run SGD and I will run SGD plus external noise, Brownian noise. We'll see what these curves are. Let's miss this. Yes. So yeah, left you have SGD and right you have SGD plus a lot of noise, Brownian. And here also we are recovering the same solution, which is the complete bipattern, balanced complete bipattern. See that it's from here up to permutations. This is nothing but the 2x2 block. Despite a lot of noise.
But it's the schedule tau n doesn't matter as long as it's going to 0. Like nothing else.
Tau n, the rate at which
Yeah, the schedule rate of like how in this now noisy once you're
I
adding.
use constant steps.
But it's very much required that step to go to 0.
With respect to n, not with respect to I.
Oh, it's have to end. Oh,
With respect to n. N is like 256 besides that. Okay, so understanding propagation of chaos in deep neural networks. Do they happen in practice? So here, what I did is I trained a neural network, which is a 5-layer neural network with ReLU activation function on 2 datasets, Paschen and C pattern, commonly used datasets. And all these, I'll say what these are. All these graphs correspond to the layers of the deep network. So at every layer you have a graphon, which is a bipartite protein graph. And I want to check the propagation of chaos property along all these layers. Every layer corresponds to a graphonic function. So what I do is I sample m cross m 2x2 submatrices from the large matrix at every layer. So that gives me 4 random variables. Now what I want to check is, are those 4 random variables jointly independent statistically? And I used off-the-shelf hypothesis testing things. So on the x-axis, n is increasing, and on the y-axis, I have the p-value of the test. The null hypothesis is essentially that the number of random variables that you are trying to test, they are jointly independent. Which means that if p is lower than let's say 0.05, they are not independent. And as p is increasing, maybe they are independent. And in all these layers and all different 2 data sets, what we are able to see that the p-value increases as n increases, which kind of means that there is this propagation of chaos phenomenon in deep networks also, despite the fact that we are using ReLU activation functions. And if you notice, the gradient of the ReLU is a discontinuous function. So the velocity is not continuous, and despite that, we are somehow able to see the propagation of chaos phenomenon.
So this is the characteristic thing. So the null hypothesis, they are independent or they're not?
They are independent. So when p is low, you can reject the null, which means they are independent. So for small values of
But you just failing to reject the null. That's all that.
yeah, I just reject that. If p is high, I am not very sure if I can reject that. Maybe the null is true. Maybe.
Yeah, but it's like not the usual way we will do. Like, so this is like saying that my hypothesis test failed. As in I could not
If p
reject
is
that.
low, then I could not reject the null hypothesis. And the null is that
But I could not reject it at some very small, like instead of 0.5, I get 0.10. It's
yeah. So and we see a monotonic.
yeah, with n. Oh, I see. That's so.
X is in log scale. So
So maybe it was even higher, but n is going to be very large.
So it hints the fact that maybe in the real world setting, for a real world data set, for a discontinuous, non-differentiable activation function also, you are able to see this propagation of chaos phenomenon. in some experiments. All right, so what are the takeaways on this work? So we have a family of randomized algorithms. All these algorithms could be random. The randomness can be from the data, could be from external. But all these randomized algorithms have the same a smooth deterministic limit on the space of graphons. So the curves that I described, the gamma t curves and the W curves, whatever, they are smooth deterministic functions, curves. Something non-trivial, but a nice thing to note. The next part, as I was saying earlier, geodesic convexity is the set of functions which are geodesically convex is strictly bigger than the set which are just completely convex. In the setting of the two-layer neural network case, people have shown that under certain conditions on activation function and data distribution, the risk function of a two-layer neural network boils down to be a geodesically convex function with respect to the Wasserstein metric. And we always hear that neural networks are naturally non-convex, but if you choose the right metric, you're exploiting the invariance symmetries, maybe you can lift your notion of convexity and deal with them easily. In the limit, we see a propagation of chaos phenomenon over processes of graphs or matrices, which I just described earlier. And the takeaway which I like the most is that this is like an attempt to generalize the Wasserstein calculus for higher order exchangeable structures. And why I say higher order? Because in the particle setting, this is like a 1D system of particles. And you are only allowed to permute the particles just like that. But when you are permuting a graph, you need to permute the rows and the columns both. So you get bigger and bigger dimensional arrays, and maybe this is just an attempt to extend or make sense of Wasserstein-like calculus for these higher order structures. Now, for example, we do have reading those now on graphons.
So graphons are always in 2 dimensions or can they be in multiple dimensions?
You mean hypergraphons?
Double
They exist. They are the limits of hypergraphs. The notions of cut metric also extend. And there is not a lot of work, but still they have been defined.
If you have multiple there in neural networks, you might get a hyper graphon.
You don't have hyper edges.
You don't have it, right? That's true.
But there is a symmetry. I'll come to the next one. So in future direction, we try to do something very similar for deep neural networks. Now here, the way we are looking at is this: we will use a graphon at every layer, which would be a bipartite graph, and it will respect the joint layer-wise permutation symmetry. Because the previous layer and the next layer are like dependent on the permutation that you use to permute the neurons. Using that symmetry, if we are able to create a limiting object, we call them chain graphons. It's the sequence which is like entangled. That would be the limiting object, and the hope is that everything can be done on that space also. Nothing really changes. It's like tensorization of this concept. One thing is that what this work is in progress. The theory of graphons was developed for unweighted graphs, that is for like 0-1 adjacency matrices. And we used the topology for 0-1 graphs on weighted graphs. And because of that, we lose the topology that we end up getting, which is the cut metric or the graph convergent topology, is a little bit weaker. And so we want a stronger notion of a natural topology, which captures the weight aspect of the graphs. A very simple example, like we saw the Ardot-Renyi example that Gn half converges to the all constant half graphon. Consider another sequence, which is the all half matrix. That also converges to the same graphon. So that topology is not able to distinguish between these two sequences, the limits of these two sequences, because it was not developed to do that. And in order to do that, we need to capture the distributional aspect of the weights. And one attempt is to work with measure value graphons. By that, what I mean is that instead of graphon being a function from 0-1 square to real numbers, we would like them to be functions which take values in probability distributions over real numbers. That will capture the weight aspect of the edges. And trying to build a topology around it so that these trivial examples don't really occur. Then there are some open questions which we don't have much clue to work with at the moment. So in the deep neural network setup, we have a data distribution which is fed from the left, for example. And the distribution gets put forward layer by layer, and it's like a sequence of distribution which propagates to the depth, and then it gives you a distribution on y, so that y hat of x and y are close point by point. So understanding that how does this data distribution gets propagated across the depth, it looks like a control theory problem in the optimal transport setup, but we are yet to make this formal and make sense of this question. And if you are able to do that, maybe there is a way to take limit in depth, very, very optimistic, maybe. And but by limit in depth, I mean taking depth to infinity somehow. Next is what can we do for sparse graph? Is there a notion of gradient flows on sparse graph which are amenable to Euclidean-like algorithms? There are people have studied limits of sparse graphs, and they are called graphixes and graphings and so on. But the main challenge is to have an L2-like structure on that space so that we can make sense of what a gradient would look like, what a gradient flow would mean, and on the space of limits of sparse graphs, whatever the limit is. So these are some future directions, and
Can you go to the previous slide? So, could you explain again what you mean by Euclidean convex functions are subsets of geodesic functions?
I mean that there can be functions which are not convex in the Euclidean sense, but are geodesically convex in the delta 2 metric that we use.
No, but the delta 2 metric is not a Hilbert space, right? I mean, the space on which you're looking at functions, that's not a Hilbert space.
It's a metric space.
It's a metric space. So what do you mean by Euclidean convex together?
So geodesics are well defined on that space.
Okay.
And along geodesics, if you test the convexity relation,
Okay.
then that becomes geodesically convex. If it is convex along that
So that what do we Euclidean convex together?
straight lines. Take that matrix
without the
without quotient. Yeah. There it doesn't really make sense to take adjacency matrix of one graph and other adjacency matrix of a different graph, in whatever way they are labeled, and take convex.
So that's not very defined then, because you can depending on the computation you get
That is a big source of non-convexity in neural networks, because there is an invariant that leads you to a lot of redundancy. For example, if there is a local minima basin, for example, there are n factorial ways to permute the neurons. There will be replicas of the same basin all over in the Euclidean space. But if you quotient that out, all those basins are equivalent. So this very trivial source of non-convexity is gone here. And once we have geodesic convexity, which is easier to achieve because of this, you can use your optimization analysis to make sense of convergence and so on. Any questions?
Thanks, Peter.
Just